Let's now do a little bit of string theory.
Is this the idea that it's meant to be a theory of everything, unifying classical and quantum?
It's unifying general relativity and quantum. In quantum mechanics, my favorite picture is Feynman's picture, the field picture of quantum mechanics. The way we understand the interaction between particles in quantum mechanics is that they exchange virtual particles. So here what we see is an electron that's being deflected by an electron. You know, electrons repel each other.
Like
That's the
magnets.
classical picture, right? In the quantum picture, the reason why they get deflected in opposite directions is because they're exchanging a virtual photon. Okay, and that's what you're seeing in that Feynman diagram. An electron is coming from the left, an electron is coming from the right, and they're exchanging a virtual photon, and that's how the momentum gets transferred from one to another. In string theory, there's no longer anything called particles. Instead, all of our fundamental particles, all of our fundamental fields are made out of one-dimensional strings. So you can imagine a rubber band that's one-dimensional. It's a line, and that line oscillates in multiple dimensions. Okay, just like a guitar string can oscillate, you know, this way or into the guitar and out of the guitar. So that's two dimensions that it's oscillating. A string can oscillate in multiple dimensions, sometimes 10, sometimes 12, depending on what theory is your favorite. Okay.
And the idea here is that as you break down to smaller scales, molecule, atom, neutron, strings are smaller
Than that,
are the most fundamental atomic unit of physical reality.
The beauty of string theory is that it's all just one string. There's no such thing as all these different fields and all these different particles. There's only one fundamental thing, and that is the one-dimensional string. And the way that it moves around in these 10 dimensions gives it the properties of an electron or an up quark or a down quark and all these things. So it's a nice like mathematical unified picture.
That's interesting.
It just hasn't found any real world physics use cases, because in order to prove whether these strings exist, you need to go down to the fundamental scale, like the Planck scale, of really tiny length, really tiny time. The energy is massive, 10 to the 19 giga electron volts, which, you know, the LHC only has 10 to the 4 giga electron volts. So we're trying to do 10 to the 15 on top of what the LHC at CERN is doing.
The Large Hadron Collider, for those who might not know.
That's right. Yeah, the LHC is the Large Hadron Collider. So we need a LHC the size of the galaxy in order to probe these limits.
This is very largely theoretical because as of yet, there's been no way to experimentally play with these theories.
Exactly. Yeah, exactly.